Hello students, this video is designed to help with the problem sets from lessons 7 and 8. I also have the problem set from the extra practice lesson that we did on coordinates. Hopefully this will be helpful to you. You should try the problem set first, pause the video, and then come back to it when you're done. There were a lot of proofs in this one. This first proof was obviously very short. We're trying to prove that shapes are parallelograms here, and we have a number of different ways to do that. We can say that the diagonals bisect each other. Here, we claim that there are two pairs of opposite congruent sides. That's another method of proving parallelograms are in fact parallelograms. In this one, opposite angles are congruent. That's another method of proving that parallelograms are in fact parallelograms. So these were very straightforward proofs. All right, moving on to the next page of that problem set. That's problem set lesson 7. Again, pause the video, give these a shot, and then see if you can get them right. All right, taking a look at this first proof, it was significantly longer than the previous proof, but it was the same basic idea. We're trying to prove that ABCD is a parallelogram. Eventually, we want to get to one of these 5 methods of proof. One pair of sides is both congruent and parallel. The other ones are two pairs of sides are congruent, two pairs of sides are parallel, two pairs of opposite angles are congruent, or the diagonals bisect each other. Diagonals bisect each other is my favorite. Anyway, this one should have made sense to you. We talked about subtraction property of equality here and the subtraction postulate, which we learned about in class. There was a whole lesson on that. For this next one, for question number 5, is a lot shorter. We were trying to prove that two pairs of opposite sides are congruent. As soon as we're given information enough to prove these two triangles are congruent, we could easily find the rest of it through CPCTC. All right. Next, I want to take a look at the extra practice problem set. This was the problem set from the extra practice document where I asked you to come up with your own coordinates for these different shapes, trapezoids, isosceles trapezoids, parallelograms, etc. What I'm going to do is I'm going to show you my versions of these shapes. You didn't have to pick these particular coordinates. You could pick any coordinate that you wanted, as long as it made the shape that was requested, and then you had to prove that the shape was a trapezoid or a parallelogram or whatever it was using coordinate geometry. So pause the video, try it out by yourself, and then see if you did it right. Looking at this first one, I called it trapezoid bear, B-E-A-R. I gave the coordinates here. Again, you didn't have to pick these coordinates. You could pick any coordinates you wanted, but a trapezoid is a quadrilateral with one pair of opposite parallel sides. So we proved these two sides were parallel by finding their slopes. If this slope is 1 and this slope is 1, so that means this BE is going to be slope of 1, this AR is going to be slope of 1. Looks like we got a trapezoid on our hands. For number 2, isosceles trapezoid, again, you didn't have to use these. I used L, I, O, and N, spelling out lion. L, I, and O, N were obviously parallel to each other, but I had to prove that using the two slopes. You know that a horizontal line is going to have what's called a zero slope. If it was a vertical line, it would not be 0 over a number. It would be a number divided by 0, which would be undefined. And it's okay to have an undefined slope. That just means a line that is vertical. In any event, these two were the same slope, so that means these two sides are parallel. And in an isosceles trapezoid, one pair of sides has to be parallel, and the other pair has to be congruent. These are also known as the legs, LN and IO. You were able to do the distance formula to find that out, and both of those gave you a distance of 5. I set it up so that it didn't give you a decimal, but it wouldn't matter if it did. If it gave us the square root of 24, for example, it would be an irrational number. If this had the square root of 24, it wouldn't matter what kind of number it was, as long as they were the same value. For number 3, we asked for a parallelogram. This was my parallelogram, WOLF. I know it's a parallelogram because it's got one pair of sides that's both parallel and congruent. Here's the proof for congruent. Like I said before, it doesn't matter what the decimal form is of this square root. As long as this says square root of 73 and this says square root of 73, they are congruent. And then we proved that those same two sides, OL and WF, were going to be congruent. Going to be parallel by looking at their slopes. 8/3 is the slope of this one. 8/3 is the slope of this one, otherwise known as 2 and 2/3, or 2.6 repeating. In any event, these are the same, so we know that they're parallel. So one pair of sides that is parallel and also congruent. The next page asks you to find rectangles, rhombuses, and squares. The square was probably the easiest one to do, but all of them were fairly straightforward. It was pretty boring if you just made a shape that was orthogonal. In other words, if you just made a shape which was, horizontal lines and vertical lines. Pretty boring, gang. You were trying to, you're trying to find lines that were diagonal in some way. So this is a pretty boring example of a square, but I'm going to show you a more interesting one. Pause the video. See if you can get some sample coordinates, and then see if you solved it the same way that I did. All right, this first one, I named it rectangle FISH for fish. This side and this side were congruent because I found their two distances, their two lengths, and I found that they were the same. So that's FI here and SH here. I also found the slopes of these two sides. It was FI is slope -1, SH is a slope -1. So it's got one pair of opposite sides that are parallel and also congruent. That means it's a parallelogram. But a rectangle is a special kind of parallelogram, one in which they have two pairs of consecutive perpendicular sides. In other words, this angle has to be a right angle. In other words, we need, for example, FI and FH to be perpendicular to each other. So we found the other slopes. It turns out that this slope and this slope are what's called negative reciprocals, which in other words, whatever this slope is, you flip it upside down and turn it to the other sign, and it becomes negative reciprocal. Same thing here and here, which means these two lines are perpendicular to each other. Not only are they perpendicular to each other, but they're perpendicular to each other's perpendiculars, if that makes sense. Like I know that FI and IS are perpendicular, which also means that FI and FH are perpendicular because this line is perpendicular to both of the other sides. Once I find that they're perpendicular, I can say that it's not just a parallelogram, it's a special kind of parallelogram with perpendicular sides, and that's called a rectangle. For number 5, it asks us to find a rhombus, and I did a boring little horizontal one for this rhombus. It was just bird, B-I-R-D. I used a special method to prove that there were parallelograms by using the midpoint formula twice. Now you might think to yourself, well, this is kind of cheating. You can't just find two midpoints and call it a day. It turns out that if you can find the midpoints of these two diagonals and they're the same exact point, that means they meet at that midpoint. That means they bisect each other. Bisect each other means they meet each other at each other's midpoints. So it's a little short version of trying to prove that two diagonals bisect each other. A short way to prove that it is a parallelogram. Then what I did was I found the length of BI and the length of IR. I found that they were the same. They were both 5, which means they're consecutive congruent sides. Well, I already know it's a parallelogram, so I already know that BI is congruent to RD. If I can successfully prove that BI is congruent to IR as well, that means it has to be a rhombus because all 4 of these sides have to be perpendicular. I'm sorry, they all have to be congruent. Whew, good save. Question number 6, it was mule, M-U-L-E. It was a square, and I found out that it was a square by finding all 4 of the sides. Now, you might think to yourself, well, all 4 of these sides are congruent, but that doesn't necessarily mean it's a square. It also means that, what was I saying here? It also means that it's a rhombus. Well, in a square, it has to have one other special property. Since all of these have congruent sides, you also need to know whether there is a perpendicular line. A perpendicular angle, or 2 perpendicular lines. So what we need to do is figure out whether ME and MU are going to be perpendicular or right angled. Here's that calculation. Once I found these two slopes, I found that one of them was -1/2, and one of them was 2/1, which means they are negative reciprocal slopes. Negative reciprocal slopes means that they are perpendicular. So all I need to do in order to show that this is a square is to first prove that it's a parallelogram, second, to prove that all of the sides are congruent, that makes it a rhombus, and then I need to prove its rectangularness, because, as you know, a square is a rectangular rhombus. I need to prove its rectangularness by proving one of these angles is right. Why only one? Well, if I know that this one is a right angle, I also know that this one is a right angle, and I also know that this one is a right angle because of the properties of a parallelogram, and I know that this is a right angle as well. All right, so just one was necessary. Moving on, this is the lesson 8 problem set wherein it was proofs about parallelograms. It doesn't tell us it's a parallelogram here, so we're going to use those 5 statements to figure out whether it's a parallelogram, and then some of them it tells us it's a parallelogram, but then we have to prove that it's a more special kind of parallelogram, for example, a rhombus. As you saw on the first slide of the video here, if I know a shape is a parallelogram, it could still be a special kind of parallelogram like a rectangle or a rhombus, and square is the most special kind of parallelogram. Anyway, let's go back here. I'd like you to pause the video, try these proofs out, and see if you get them right. All right, taking a look at the Lesson 8 problem set, an easy way to start this proof is to draw the triangles separate from each other. This is triangle AEF, and this is triangle CEG. I know that they're going to be congruent to each other because of 3 different reasons. Reason number 1, we're given that DAE is congruent to BCE. So those are those blue marks. Reason number 2, as soon as we prove that this is a parallelogram, we can use the diagonals bisect each other idea to say that AE is congruent to CE. Reason number 3, I know that these green markings are here because of these 2 angles being vertical angles. So angle side angle is my objective. You can see in the proof that I built up the fact that it was a parallelogram because it's got 1 pair of congruent parallel sides. Then I stated that E is the midpoint of AC because of parallelograms, and then AE is congruent to EC. That was what I said for my second step. My third step, I said that these were vertical angles, which is very straightforward, very easy, and then ASA postulate for these 2 triangles being congruent. For number 2, we were given that it's a parallelogram, so we have all the cool stuff about parallelograms already locked and loaded, but we don't know whether these 2 sides, these 2 consecutive sides, are going to be congruent. So what we had to do was, we had to use the transitive property. Here we said JM is congruent to LN. Here we said JM is congruent to LM. Once we're done with that, we need to identify the ones that they have in common here. What side do they have in common? Well, I know that JM and JM is the same for both. So that means that LM and JM are going to be substituted with that transitive property. Finally, we can say that JKLM is a rhombus because as soon as we have 1 pair of consecutive congruent sides, we know that it is going to be a rhombus. All right, for number 3, it was asking us to prove that AE is congruent to BF, so you could probably guess that we're going to first try to prove that triangles are congruent and then try to get CPCTC to say that AE is congruent to BF. That means I'm looking for where AE is and where BF is and then trying to figure out, well, what triangles are they part of? Well, I see this triangle here, this right triangle, and I see this other right triangle, both triangles that are indicated in the proof, FAD and EBC. Very straightforward to prove that these triangles were congruent just by using ASA postulate. I know that these angles are given to us. I know that these 2 sides are congruent because of it's a rectangle, and I know that these 2 angles are congruent because, again, it's a rectangle. Then I'm using my subtraction property of equality. That subtraction property of equality is used when I have 2 pieces that are equal to each other. I know that AF and EF are going to be congruent to BE and EF because I know AF and BE are the same, and I know that EF and EF are the same. So that's another use of that subtraction postulate that we talked about in class. Coming up to the last page here of the last problems that we're going to do, pause the video, see if you can try these out, and then come back and check your work. All right, this first proof was I always say they're very straightforward. In this case, we're given a bunch of information about a quadrilateral, and we're asked to prove that it's a parallelogram. I used my favorite method here, that diagonals bisect each other. And once I am able to prove that these 2 triangles are the same, I have diagonals bisecting each other very easily. The triangles were the same because of angle side angle. We knew angle side angle was present here, and then we were able to prove that these other 2 sides were corresponding parts of congruent triangles, so they must be congruent. That's what CPCTC stands for. For number 5, it was given to us that it was a rhombus, and we had to use our subtraction postulate yet again to get these little angles here. We were trying to prove that these little triangles were congruent so that we could get TX and TW, which were these little wings out here. We were able to do that using CPCTC. And then finally, this one was the longest proof of the problem set. It was 12 steps. If you can do it in fewer steps, let me know, and I might post a follow-up video about this. But anyway, you needed to do a little bit of work for this one. It's one of the classic proofs that isn't always taught in school, and certainly this exact proof won't be on your Regents exam, but it is something that definitely uses all the stuff you know already. All right. This video was designed to help you out with the problem sets from lessons 7 and 8 and the extra practice. Hopefully this was helpful to you. Good luck studying.